Alright, in this video here we're going to be looking at some more applications of integration. So we're going to be looking at, in the next 3 videos, arc length of a curve, and then also surface area for some sort of curve rotated around an x or y axis, for example, and we calculate the surface area. So to start off, we have the distance formula. Sometimes it's called the Euclidean metric in the real numbers. The real numbers cross the real numbers. So the Euclidean metric is just the standard distance formula metric for measure. R cross R is just the xy plane. So the distance between 2 points in the xy plane, Euclidean geometry, we're using the Euclidean metric, which is just the distance formula. So the distance between 2 points, A, which is x1 comma y1, and B, which is x2 y2, the distance between points A and B is going to be the square root of x1 minus x2 squared plus y1 minus y2 squared. Okay, a rectifiable curve is a curve with a finite arc length. We will only be considering rectifiable curves. These curves are continuously differentiable, or maybe like piecewise smooth. An example that you saw probably in Calculus 1, something that is not rectifiable, is y equals the sine of 1 over x. And you can see the graph there. It has an infinite oscillation between minus 1 and 1 as you approach 0. So that does not have a finite arc length, and so we'd say that's a non-rectifiable curve. Okay, so we're going to be looking at rectifiable curves. So if we take a rectifiable curve, so maybe we can sketch a little bit of an example of a rectifiable curve. Okay, so we'll just do in the first quadrant. So a nice smooth rectifiable curve like that. So if we take a rectifiable curve on a closed interval AB, so there's A, there's B, and then what we're going to do is we're going to form a partition. So A is going to be equal to x naught, and then we'll have an x1 and an x2 all the way out to xn, which will be B, and we're just going to partition that interval up. Okay, and we're going to apply the distance formula to each consecutive pair and call that distance delta xi for the difference in the x coordinates, and delta yi the difference in the y coordinates. And so what we're going to do is we'll start here and go to here, and then we're going to find that length, that line segment length, and from here to here we're going to find that line segment, and then from here to here, and etc. And we're going to add up all those line segments, and all those line segments are going to approximate the actual length of the curve. For convenience, the difference in the x-coordinates is delta xi, difference in the y-coordinates is delta yi. And add up all these distances, so the purple one, the blue one, the green one, etc. We're going to add those all up. So down below you have S, which is your arc length, is approximately equal to the sum, I equals 1 to n, of the square root of xi minus 1 squared plus yi minus yi squared. And that's just adding up each one of these line segments. Okay, so we're just going to add this line segment, this line segment, this line segment, etc. Okay, and then in the next summation here, we replace the xi minus 1 with delta xi and delta yi. Okay. Then in the next step here, all we've done here is we've really multiplied and divided by delta xi squared. So you see here's the numerator, and then here's the denominator, delta I squared. So we haven't changed anything, we just rewrote it that way, and we'll proceed to the next slide here to kind of see where this is going. So there's that last line on the bottom of the page. It's here again. And so we can go ahead and say we have delta xi squared, okay? And then that's going to be times the 1 plus delta yi over delta xi squared, okay? And so you can use a property of the radical, which is the square root of a times b is equal to the square root of a times the square root of b. And so then we're going to take the square root of the delta x squared there, and so that's going to come out of the square root. So we see it right there, okay? All right. Now the idea is we use more points in our partition, so we have very close points on the curve, so that the line segments that we're finding the length of is going to be very close to the actual arc length there. And so we say if we let the norm of the partition go to 0, the number of points we're going to use in our partition n will go to infinity, and our approximation will get increasingly better. We can apply the mean value theorem to each one of those subintervals. So, here's a subinterval, and then remember the mean value theorem said that here's your tangent line, okay, and that is going to be the same as the secant line connecting those 2 points. So the mean value theorem says that there's a point of tangency where the slope at that particular point is the same as the secant slope. So that was your mean value theorem. So we can apply the mean value theorem, so MVT, to each interval, xi minus 1 to xi, and there is a ci in each interval such that, and this is where the mean value theorem comes into play, so f prime of c of I, so that would be the slope of this line up here, okay, is equal to f of xi minus f of xi minus 1 all over xi minus xi minus 1, and that's just the slope of the secant line there. And then we can call that delta y over delta x. So our arc length S is approximated by, okay, sum I equals 1 to n, f plus, and so what we're going to do is we're going to use f prime of c sub I squared because of the mean value theorem, okay, so that gets the derivative involved, and then times delta xi. And so we can define the arc length to be the limit of this sum, so the delta xi becomes the dx, the f prime of c sub I will just become f prime of x, and so you have your arc length formula there. So here's our arc length formula. Okay, and we can do this either in terms in terms of functions of x or functions of y. So then it says for smooth curves, y equals f of x on the closed interval AB, or x equals g of y on the closed interval CD. The arc lengths are given there, so depending on if you're doing functions of x or functions of y. Okay, so in this video we're going to do 2 examples of finding the arc length, and then the second video I think we do one more. So let's go ahead and look at the next page here. Okay, so we're going to find the arc length of y equals 3x minus 5 on the closed interval 0 to 3. And you might say, well, this is just a line. So if you're going to find the distance between 2 points, well, they're on the line, so you can just use the regular distance formula. So we'll do that at the end there. So we'll go ahead and write down our arc length formula. Okay. And so we know what our limits of integration are. They're 0 to 3. The only thing we need to do is find y prime. Okay, so y prime is simply 3. So install that in. So you can put the 3 and square it in there. Okay, so that's going to give you a square root of 10. And you can go ahead and slide out the square root of 10 out of the integral. So we have the square root of 10 integral from 0 to 3 dx, and that's a 1 dx. So it's going to be the integral of a 1 is an x. So x square roots of 10 evaluated from 0 to 3. And that's going to give us 3 square roots of 10. Okay, which is approximately 9.4868 units. Okay. Now, I also said that we could use the distance formula because this is just a line. So we need to find the two ordered pairs. So to find the ordered pair that goes with 0, plug that in for x. And so the y that goes with 0 is -5. Then plug in the 3. So the y that goes with x equals 3 is 4. So that gives us the ordered pairs, 0, -5, and 3, 4. The regular distance formula is the square root of x1 minus x2 squared plus y1 minus y2 squared. So that's going to be 0 minus 3 squared plus -5 minus 4 squared under the square root. So that's going to be 9 plus 81, which is going to be the square root of 90. So the square root of 9 times 10, so that's going to be the square root of 9 times the square root of 10. So that gives us the 3 root 10, and so we were able to get that as well. And this was just a line segment, so that'll work fine. But let's do an example where we have a curve here. Okay, so this time we're going to find the arc length of y equals 3 x to the 3/2 power. And we're going to do it on the closed interval 2 to 3. So the arc length formula is there. So y prime, 9/2 x to the 1/2. Limits of integration are 3 to 2. 1 plus 9x to the 1/2 quantity squared dx. So that's going to be integral from 2 to 3. 4 over 4 is 1. 4 over 4 is 1. Okay, plus 81x over 4. Okay, so that's going to be the integral from 2 to 3 of 4 plus 81x all over the square root of 4, using properties of square roots. The square root of 4 is 2, that's in the denominator, so we're going to slide the 1/2 out. Integral from 2 to 3 of 4 plus 81x. Okay, so we can do a simple u substitution. U is 4 plus 81x. Du is 81 dx. Solving for dx, we have du over 81 is dx. So this becomes 1/2 integral. Let's convert our limits because we're doing a substitution. So x is equal to 2, so u is equal to 4 plus 81 times 2. So 166 is our new lower limit. Original upper limit was x equals 3, so u is equal to 4 plus 81 times 3. So 247 is our new upper limit. U to the 1/2, du over 81. So it's going to be 1 over 162. Then we integrate, and that's going to be u to the 3/2 divided by 3/2. We're going to evaluate that from 166 to 247. It's going to be 162 over times 2/3 because we flip the 3/2 over that we're dividing by. Okay, and so we're going to get 7.1735 units there. And on this last slide here, I went ahead and graphed the 3x to the 3/2 power. Now 3x to the 3/2 power, 3/2 is the same thing as 1.5, so it's the same thing as 3x to 1.5. And you know, here's your 2 points there. So you're finding the arc length between those 2 points there. I went ahead and used the distance formula. And so we got something that's pretty close to the actual arc length. I think they're off by the what was that? The thousandths position is where we're off, and because this graph is between those 2 points is fairly close to linear there. The distance formula is pretty good. Now, what we were mentioning earlier is if we wanted to make this a better approximation, we'd find the length here, here, and we just go all the way there, and we'd find the lengths of all of these little pieces here, and we would, to get a better and better approximation, we'd use more and more points, so your x values are getting closer and closer to each other, and that's your delta x going to 0 there, your normal of your partition going to 0, the end going to infinity, all of that. So anyways, that's pretty much it for this video. Stay tuned for the next two on arc length and surface area for I guess we could say volumes of not volumes of revolution, but a region that we're going to rotate around the x or y axis. We'll find the surface area of that. So we'll see you next time.